Okay, today we're going to take those dot diagrams that you had started before, how you put the valence electrons in the dots around the symbol. We're going to take those and we're going to start bonding them together, hooking things together. Now, we're going to start with the ionic bonds, so ionic dot diagrams. And in these, the electrons actually come off of one and go on to the other one. So this one's ionic bonding. When electrons come off of one and go on to the other, it's called transferring. So they transfer valence electrons from one atom to another one, which basically turns them into ions. So one of them will gain electrons and one of them will lose electrons. I mentioned before that in the periodic table unit, the last unit, that metals lose electrons and nonmetals gain. So you could look at the periodic table and figure that out. But there's an even easier way to tell than that. Of the two elements you're looking at, whichever one has less electrons, it's going to want to get rid of them. Whichever one has more, it wants even more. So take them off the one that have less and put them on the one that has more. And you can restate that to say, take them off the one that has less and put them on the one that has more. These notes are for you to help you to remember what's going on and how to do it. Remember also to look around and make sure nobody's using electronics that they're not supposed to be. If they're taking notes on their iPad, that's one thing. But if their phones are out or their earbuds are in, you can call them out and get extra credit for having called them out. And they will have to bake cookies. So we're serving attention, and there's a whole bunch of dishes sitting on the back heater that need washed. So that's a possibility as well. But anyway, help hold each other accountable to following along, because if you're not listening and you're not paying attention, you're not going to know how to do these problems. All right, so on the next slide, we're going to start how to actually work the problem. So get ready. Okay, right now we're going to draw dot diagrams for ionic bonds in ionic compounds. To do that, you're going to need different colors. So if you have different color highlighters, pens, pencils, um, that's great. You need 3 or 4 of those. Um, if you do not, then I have a whole tray full of colored pencils that I sharpened right before I left. Um, go get 3 or 4 of those and uh, bring them back to your desk. Try and get colors that you can see. So obviously not white on the paper, and also ones that are very obviously different colors than each other. So don't give me 3 shades of blue or 3 shades of brown. You know, choose like blue and orange and green, something like that, where they're really different from each other. While you're doing that, I'll put up just like a short description of how this is going to work. So when you get back to your seat, um, go ahead and write down what's on the screen so far. It's really hard to figure out how long it takes you to get up, go to the colored pencils, and get them with a bunch of people doing it at the same time. So we'll take a commercial break. What books do you like? Let's see. Hmm. I really like books. I have a like. It depends on the mood I'm in. Like could be fantasy or survival or romance or mystery. Mystery is definitely one of my favorites. But anyway, um, one of the best books though that I really liked or enjoyed at the time was, well, of course, Harry Potter. That goes without question. But the classics, the I really like a good series because if you if you get a good one, then those people just they come a part of your life, and you get to know them as if they are actual people in your life. And so then you get to see them again or meet up with them again in the next book. So I really like series like that. But anyway, one of the books I liked that I read fairly recently was a uh, book about an EMP strike, an electromagnetic pulse strike, that knocked out all the electronics in the world. And it was just a really cool book to hear how they coped with that. And it was called, I think it was called Going Home, either Going Home or Coming Home, one of those two. And it was by, you could tell that the author's name was a pseudonym because it was by A, as in his first name was initial A, American. So it was by an American. There you go. So anyway, hopefully by now you've gotten the colored pencils and you're headed back to your seat and you're starting to write some stuff down. All right, I'm going to go ahead and start. If it's too soon, you can always have the sub back it up somehow. And if it took me too long, I apologize. So you're going to draw an equation. So you're going to have something plus something, make something else, basically. So um, we're going to use NaCl as our example compound, and we're going to draw dot diagrams. So we'll just draw a dot diagram for sodium, and then a dot diagram for chlorine, and then just put a plus sign in between. So here's the directions on what to do, and then we'll do it with the example. I hear an airplane going by, airplane, helicopter, or something. And so I'm just sitting here wondering, I wonder if they can hear that. Okay, so once again, you take one color, draw NA, decide how many dots to put with it. Remember, you do that by looking at the periodic table, the top of the column with the number with the A behind it, That's how many valence electrons it has, so that's how many dots we put. So Na is in group 1A, so we put 1 dot. Then draw a plus sign. Then draw Cl. It's in group 7A, so it gets 7 dots. So in the middle there, so that's what that part should look like. Then you draw an arrow after your last one to show this is what, so basically this shows what they look like before, and then we're going to draw an arrow and show what they look like after. Okay, now we're going to do what I said before, which is to take them off of take dots off of the one that has the least amount and put them onto the one that has the most amount. So I'll let you write that part and then we'll actually do it to our example. By the time we're done, either one of them will be showing 0 dots and one of them will be showing 8 dots. So it's going to look something like this. So see how I took the blue dot off of sodium and I moved it over to the chlorine. But I still kept it blue because that shows that that dot came from the sodium. So it wasn't a natural part of chlorine. It wasn't there all along. It came from sodium and it went to chlorine. And by color coding, I can show the teacher or whoever's reading this that that is what's happening and that I know that that is what's happening. If you just draw 8 black dots around something, I have no idea if you just knew that it came from sodium and went on to chlorine, or if you were just throwing 8 black dots around everything. So by color coding it like that, you're showing me that you know where it came from and where it went to. So if the dot that you moved starts out blue, it needs to be blue at the end. It just moves from one atom to the other. Notice now, sodium has no dots around it, which means whatever its valence energy level was, which was 3, that's now empty, which means energy level 2, the one before it, is now its new valence level, and that valence level is already full. So it really has 8 because it's dropped back, but we don't show that. Okay, the next part I think I'll let you write, and then I will explain what it means, because once you have it written down, you'll be able to focus on what I'm saying, I think. I hope, maybe, possibly. If you're listening. Maybe nobody's out there and it's an empty classroom. Better not be an empty classroom or you guys are in big trouble. This applies to the right of the arrow only. You do not do anything else to the left side before the stuff before the arrow. So step number 4 is referring to after the arrow only. And you'll see that when I pull up the example. Okay, so here's what I'm talking about. Notice that on the right hand side are the brackets and the charges, only on the right hand side. On the left hand side, it has to look like they originally would have looked before they reacted. On the right hand side, you're showing what's left after they've connected. So um, that's the brackets and the charges. The brackets mean that we have moved electrons either away from this atom or we've added electrons onto this atom. So the normal natural amount of electrons we have manually changed. So it's just a way of showing that, yes, we know sodium doesn't really have 0 electrons. We moved one. And then because you took an electron away from sodium, it now has one more proton than it does electrons, so it's a +1 charge. So if you take an electron away, it's a positive. If you take 3 away, it's a +3. If you add electrons on, like we did with chlorine, then it's negative. So if you added 6 electrons to it, which hopefully wouldn't happen, but if you did, then it would be a -6 charge. Here we only added 1 electron to it. It had 7 of its own originally, and we just added 1. So it's a -1 charge. So remember, when we add and take and remove, that we're adding and removing negatively charged things, which makes it kind of backwards. So basically what we're showing here is we've changed the number of valence electrons around this substance, and that's what the brackets say. And then the charge tells them basically how many and what we did with them, either add or subtract them. This next part is kind of, you can put it there and you really don't have to. What happens then is the positive one attracts to the negative one, and that forms the bond. But it's also okay to put the plus sign in there. Uh, in between the new sodium and the new chlorine, like this. So you can do that. You don't have to. But you should put them on the left-hand side, because on the left-hand side, they haven't reacted yet. They haven't connected yet. On the right-hand side, you can put the plus sign, or you don't have to, because the positive and the negative are going to attract to each other and form a bond anyway. So either way on the right-hand side, but you should put it on the left-hand side. And that, my friends, is how you draw a dot diagram for an ionic compound. Now what I'm going to do is I'm going to put a video up of one of the ones from your homework so that you can see it. And if you have time right now in class, your teacher can show it to you. If not, then you can go on Canvas later, go to our class, go to announcements, and there'll be an example from the ionic dot diagram homework. And that will be maybe a little more complex than this one, and show you how to do it when you have more than one sodium or more than one chlorine or that kind of thing. So if you watch that video either now in class or later on Canvas, it will walk you through another one of these. So make sure you watch it and pay attention. I can tell you that the number one thing people do not do that I tell them correct and return on their papers, or I just mark it wrong, is not color coding. You have to color code in order to show us what's going on. The second thing they don't do is putting the brackets and the charge. So follow these 5 steps and it'll walk you through what to do. Okay, that's all for ionic dot diagrams. Now we're ready to do covalent bonds. Covalent bonds are different because the electrons are shared between 2 atoms instead of moving from one to the other. So there are no charges, no brackets. So with covalent bonding, you're sharing the electrons, which means any electrons in between the two get counted by both atoms. Oh, yeah, now we're outdoors in case you couldn't tell. It's a Saturday and I am up at the cottage at the lake, and it's actually warmer outdoors than it is in the cottage, so I came outside. So, welcome to the lake. Okay, so you have 2 atoms and they're side by side and there's electrons in between. So think Venn diagram type thing. And some of the electrons are shared and some of the electrons are not shared between those 2. Whatever is shared, each atom counts. So those shared electrons get counted twice as far as valence electrons and stability goes. So as you're counting dots around the outside of the symbol, anything that's shared gets counted for each one. So we're going to do the drawing of the dot diagrams for covalent compounds. And again, I'll give you a step-by-step on how to do that. What you need to do first is determine of the 2 elements in the compound, which one is your central atom, the one that all the others revolve around. And the way that you determine that is that when you draw your diagram of each of your elements, you spread your electrons out as much as possible. So one on top, one on bottom, one on left, one on right, and then double up if you need to. And then you count how many of them are not doubled up. So how many unpaired. So that's what this is going to tell you here. We'll do an example one. so I'll let you write. See how long the being outdoors thing lasts, because um, I was setting up to do this once and everybody was mowing, and so it was really loud out here. So then I went inside and I was messing around getting the PowerPoint ready, and everybody stopped mowing, so I came back out. So we'll see what happens. Okay, so we're going to do the example SI2. So we do a dot diagram for S and a dot diagram for I, and draw the electrons as spaced out as possible. So iodine has 7 dots because it has 7 valence electrons. Sulfur has 6 dots. But I spaced them out as much as I could. Now it doesn't matter whether I double them up on the sides, the top, the bottom, one side, top or bottom. Just space them out basically. So I did that. And now I can see that iodine only has 1 electron that is unpaired. Sulfur has 2 that are unpaired because I spread them out. So sulfur then would be our central atom. Now, a lot of times the central atom is listed first, but not always. Okay, once you determine what your central atom is, um, draw it in the middle, leaving lots of space around the outside of it. And then you're going to start hooking on the other parts onto it. And remember that just because you've drawn your electrons in one place on one side, those are kind of interchangeable. So if you need to move something, you can. I'll go ahead and put up like the directions, and then I'll show you what I'm talking about. So it's the Saturday before my surgery, and we're at the cottage, and so we have just this little teeny tiny little cottage on a little fishing lake. No skiing, no jet skis or anything like that. But anyway, we're trying to get as much done as far as closing up the cottage goes as possible, because then I won't be able to help after Thursday. So this is the Saturday before the surgery, just in case you're wondering. All right, so I have on here the dots to show you what's going on with this. I just would like to say that I had to type them in because the stylist wasn't writing right on the laptop screen. So just be aware that if I was drawing them, I would draw them darker so that they could be seen, and I would also draw them probably closer together so that you could tell better that they were being shared. But anyway, you can at least see what I'm doing. And also, I'm using different colors so that you can see what electron came with which one and what's getting shared. And you should do that same thing, different colors. That shows me that you know what's going on. So here I took my central atom, which I determined to be sulfur, and I just went up and down only because that's the way I had it on the screen before, so I was afraid that you wouldn't know what I was doing if I moved electrons around. So you can put them on the sides if you want. Just move your sulfur electrons around to wherever you need them to make room on your page. But you've got the left, right, top, and bottom that you can have electrons on. So this could just as easily have the iodines coming off the sides. So then I took an iodine, different color, and put that dot beside the sulfur dot that was alone, and that pair of electrons, the red and the blue dots there, they will get shared. And I'll draw circles in just a minute so that you can see the sharing. I do not normally draw the circles around them. Like, this is a completed answer to the question, but I'm going to do it so that you can actually see what's being shared. And if that's how you need to do yours to understand it, then that's fine too. So if you need the circles to help you, then draw the circles. But they don't have to be there as part of the answer. Okay, so that completed iodine, the red iodine on top, because it gets to count that blue one from the sulfur. And then the green iodine on the bottom does very much the same thing. And then if you count the ones around sulfur, sulfur now has the original blue ones it had before, plus two of the one red one from one iodine and one green one from the other iodine. So, okay, sorry about that. I forgot. It takes a little longer to draw the dots and stuff. But they're going to show up here on this slide as well. So if you weren't able to get back to them, that's okay, because they will be here on this slide. Same thing that was on the last slide also. So anyway, after you get everything on there, you check each atom to make sure it's got 8 dots around it. I always also check to make sure that it has the correct number of colored ones that match it. So iodine started out with 7, so there should still only be 7 red ones or 7 green ones, to make sure I didn't just add a dot because I didn't know what went there. So anyway, here is kind of what I just said. You have to have 8 around each one, unless it is hydrogen. Hydrogen, remember, is in energy level 1. Energy level 1 doesn't have a P, therefore energy level 1 is full with 2 electrons. So hydrogen only needs 2. It does not need 8, which is good, because it only brings 1. Helium is the same way because it's in energy level 1, but helium doesn't bond, so we're not going to run into it here. Okay, so anyway, here's what I did. This is what I had shown you before that I took away probably before you were done drawing it. But I'll show you, like, kind of circling each atom to make sure that it has 8. So I check the red iodine, make sure it has just only 7 red ones that it had before, but it gets to count the blue one from the sulfur, so it has 8. Then I check the sulfur. It has its 6 original ones, but it also gets to count 1 red one and 1 green one, so it has 8. Then I check the green one. It has its original 7 plus 1 blue one, so it has 8. So the ones that are being shared, that overlap, they get counted twice, actually. And that seems to work okay as far as being stable. Like I said, the circles or ovals or whatever I have there are not required, but if you want to draw them in, it kind of does show what it looks like. So I put them in so that you would at least be able to understand as you're learning it. And then we have ones that are more complicated, and they kind of break the rules about, two on the side, two on the top, two on the bottom. So they're a little bit different. So we'll go to that next, and I'll show you a different example with those in it. I'm just kind of stalling here in case I hadn't given you enough time on the last slide and you need to study this for a minute or look at it. I'm hoping that you can see those green dots on the screen because they show up on my computer screen, but I don't know. Okay. We moved indoors because I ran out of battery life and I have an outlet out there, but it's getting kind of noisy too, so I just moved indoors. But anyway, so I was saying that we're going to do some that are kind of exceptions. They have what we call double or triple bonds. So a single bond, a regular bond, shares 2 electrons. So a double bond would share 4 electrons. A triple bond would share 6 electrons. So, like I said, it's going to kind of push a little bit on our comfort zones on where things belong, but I'll show you what one looks like. So this is step 4. If each one doesn't have 8, so if there's one that has less than 8, then you have to do what we call a double bond or a triple bond. So sharing 4 or sharing 6 electrons. So how you know when to do a double or triple bond is when you count and something doesn't have 8. Okay, so in this example, if I just connected on oxygen onto silicon, what I would find is that oxygen would then have 7 and silicon, if I did it on each side, would end up having 6. So it's not enough around any of them. None of them are stable. So what I had to do is take some off the sides of the silicon and move them into the middle with the ones already being shared. And then I had to take one off the oxygen and move it to the middle. So then we ended up with 4 being shared in the middle, in between. So it looks like this. Oxygen gets to count the 4 on the sides separately, and then it also counts its 2 that it's sharing in the middle and 2 that silicon is sharing in the middle. Silicon counts the 4 in the middle from both oxygens. So 2 from the red one, 2 from the green one, plus its own 4. And then the other oxygen does similarly to the first one. So it's got 4 of its own that it's not sharing with silicon, and then 4 that it is sharing with silicon. So now they all have 8, and it is stable. So if you get it set up, you start setting something up, and you see, well, wait, now that one doesn't have 8. So you start taking them off of where they're not bonded to anything and moving them into the middle in between your 2 atoms until both atoms have 8. That's the only way to do it. It takes some practice and some getting used to. So on the first worksheet I left for you, I told you on the paper which ones were going to require double or triple bonds so that you would know. So just try 4 in the middle or try 6 in the middle and see what you can make it work.